SPH4U, Forces in Motion, 2.3 Solving Dynamics Problems. So there are two types of frictions. There's static friction, which prevents an object that's from moving, and there's kinetic friction, which is friction that acts during motion on an object. So static friction is given by the equation FSF is equal to Fn times mu s, where Fn stands for normal force, while mu s, that is the coefficient of static friction for the particular object. So it changes depending on the surface. Likewise, for kinetic friction is given by a similar equation, Kf. So kinetic friction is equal to Fn times mu k, where this is the coefficient of kinetic friction. And the general rule is that mu s is always going to be greater than mu k. It'll be harder to start moving a box than to keep that box moving in motion. So this is a problem that uses the concept of friction. So Nalini is at the top of an incline that makes a 35-degree angle with the ground. From there, she lets a 75-kilogram box go without any applied force. If the coefficient of kinetic friction is 0.34, what is the acceleration of the box down the hill? So first, let's draw our free body diagram. So we have this incline. We know that makes a 35-degree angle here. So we have this box here at the top of the hill. This is a force normal, force of friction back here, and down here we have force of gravity that is broken down into its components, 35. So yeah. And we will have this as our positive reference frame. So if we know that the normal force is equal to the component of gravity that is in the same plane as itself, so Fg cos of theta, Fg sine of theta. So that means that the normal force will be equal to Fg cos of theta. So Fn is equal to mg times cos of theta. So with that knowledge, we can plug these numbers into we can plug all the numbers that we have into the equation and solve for normal force. So mg 75 times 9.8 times cosine of 35. So that comes out to be 602.1 newtons. And we know that the equation for kinetic friction is equal to normal force times the coefficient of kinetic friction. So that is equal to 602.1 times UK 0.34, which is equal to 204.7 newtons. So that's the force of friction. So we're looking for the acceleration of the x direction, so F net will be equal to ma, which will be equal to Fg sine of theta, so the x component of the force of gravity, minus F of friction. So that means the acceleration is equal to mg sine of theta minus ff all over m. So now we just plug these numbers in. So acceleration is equal to 75 times 9.8 sine of 35 minus 204.7, all of this divided by 75. So acceleration is equal to, so that means the acceleration is equal to 2.9 meters per second squared down the hill. So apparent weight is the weight of an object dependent on its acceleration. So when accelerating upwards, something will feel heavier, while accelerating downwards, something will feel lighter, even weightless possibly. So now we're going to go over an example to demonstrate this. So a 50 kilogram person is standing on a scale in an elevator. What will the leading be when the elevator is not moving? The leading on scale is actually the normal force of the object upon it. So let's write down what we know. So we know that the mass is equal to 50 kilograms. You know that velocity is equal to 0. Well, acceleration is equal to 0. So what's the normal force? So let's draw the free body diagram for this. You have elevator, person on it. You have the normal force going up, force of gravity going down. This will be our positive reference frame. So since acceleration is equal to 0, the F net is equal to 0 because F net is equal to ma with a equal to 0. All this turns to 0. So 0 is equal to Fn plus Fg. That force is equal to sum of the forces, right? So that means Fn is equal to negative Fg. So Fn is equal to negative mg. So the normal force is equal to negative 50 times 9.8. So Fn is equal to 490 newtons up. It would be negative 490 newtons down, so we just converted to up. So it's 490 newtons up. So now, what will the scale lead if the elevator is accelerating at 1 meters per second squared outwards? So let's make up our positive reference frame. We know that F net is equal to ma, and that F net is also equal to Fn plus Fg. So F net is equal to 50 times 1. So that's equal to 50 newtons. So 50 newtons is equal to Fn plus Fg. So that means that 50 minus Fg is equal to Fn. So remember that Fg is actually going downwards, so it's minus negative 50 times 9.8. That's equal to Fn. So 540 newtons is equal to Fn. So if the elevator slows down at a rate of 1 meters per second squared, what will the scale lead? So for this, we can make the positive reference frame downwards. So F net is equal to ma. So that's still equal to 50 newtons. So we have F net equals to Fn plus Fg. Oh, note here that this is up. So Fn plus Fg. So that means that Fn is equal to Fnet minus Fg. So find the normal force. We do Fnet, which is 50, minus Fg. Fg is 490. So that turns out to be negative 440 down, so, or 440 newtons up. So another important type of questions in dynamics are the tension questions on a slope. So in these questions, the force of tension is actually the same. It's unified between all the components of the system. It's kind of like how time unifies the x and y components of motion in projectile motion. So in this diagram, we have all the forces that are acting on all the boxes. So since there's no friction on this, it's a frictionless scenario. So there's a force on the 5 kilogram box. There's a force of gravity that is acting downwards, and that can be broken up into its components. There's a force of tension with the lope, and there's the force normal. And then on the 6 kilogram box, which is just hanging down there, there's a force of tension that's pulled up by the lope, and then there's also the force of gravity. Note that that has a subscript 2 because the force of gravity on the 6 kilogram box is not the same as the 5 kilogram box. So the first question is, what is the force of tension? So in order to do that, we'll have to create a system of equations, and we'll have to manipulate those equations to give us the force of tension. So for system 1, which is this, we know that the mass is equal to 5 kilograms. So Fnet is equal to Ft minus Fg sine 45. So Fnet, that's equal to ma, so 5 times a is equal to Ft minus 5 times 9.8 times sine of 45. So that means that 5a is equal to Ft minus 34.6. So this is our first equation. Now let's find the equation for system 2, which is this system. So Fnet is equal to Fg2 minus Ft. Oh, we also need to set our positive reference frame. Sorry about that. So this will be our positive reference frame for system 1, and this for system 2. So Fnet is equal to mg minus Ft. We know that the mass is equal to 6, and we know the force net equation. So 6a is equal to 6 times 9.8 minus Ft. So 6a is equal to negative Ft plus 58.8. So this is our second equation. So now we can use elimination to solve for the acceleration, and the acceleration we can plug it into one of our equations to find the tension, force tension. So we do 2 plus 1. 6a is equal to negative Ft plus 58.8 plus 5a is equal to Ft minus 34.6. So that means that 11a is equal to 24.2. These cancel each other out, so force of acceleration is equal to 2.2 meters per second squared. So we can sub this back into equation 1. So sub equation 1. So 5a is equal to ft minus 34.6. So 5 times 2.2 plus 34.6 is equal to ft. So 45.6 newtons is equal to the force of tension. And we also need to find the normal force on the 5 kilogram box. So we can do that down here. So the force normal is equal to the force of gravity cos theta, because that is the component of gravity that's in the same plane as the force normal. Fn is equal to 5 times 9.8 times cos of 45. So Fn is equal to 34.6 newtons up.